Hello, my name is Carly Lossiah, and this is my presentation for Lab 3. In this lab, we learn the physics behind black holes. In this lab, we began with a star with a mass of 2.0 times 10 to the 30th kilograms that is orbiting a black hole. Assuming the only force acting on the star is gravity, we want to find the net force of the star for all data points and find the mass of the black hole. Everyone has different data points for the trajectory of the star because we used our email addresses as an input that gave us unique data. We decided that the time between each data point is 1 day. A few important formulas for this lab includes Newton's second law, which says that the net force is equal to the mass times the change in velocity over the change in time, and the momentum principle, which says the net force is equal to the change in momentum over the change in time, which equals the change in mass times velocity over the change in time. Our goal for this physics lab is to be able to predict the future and size of black holes. We will observe that the gravity of the black hole pulls the star into an ellipse-esque orbit pattern because the force continuously pulls perpendicular to the star's motion. And we will assume that the only force acting on the star is the gravitational force from the black hole. The connections with fundamental principles are as follows. A few important equations are Newton's second law and the momentum principle, which I mentioned earlier, and the net force equation, which states that the net force equals the change in momentum over the change in time, which equals the perpendicular forces plus the parallel forces, which equals the change in momentum over time, perpendicular, plus the change in momentum over time, parallel. Also, the force of gravity equals negative g times the mass of the first object times the mass of the second object divided by the distance between the two objects squared, where g is the gravitational constant. This model was chosen so that we could see the net force and the parallel and perpendicular components of the net force relative to the star and the black hole. This slide shows my edited code and the glow script output. The average mass of the black hole is about 1.13909 times 10 to the 34th kilograms. The magnitude of the net force acting on the star is 8.80441 times 10 to the 28th power. The magnitude of the net force parallel that is acting on the star is 2.37717 times 10 to the 28th power, and the magnitude of the net force perpendicular that is acting on the star is 8.48938 times 10 to the 28th power. After completing this lab, I have come up with some possible sources of error and improvements that I would implement in the future if I were doing this lab again. Some potential sources of error are mainly typos in the code, which would result in an output that is not accurate. This is not likely, but it is always possible to make a human error. As for future improvements, I could have made my code make the arrows for the forces larger or more distinct at all times. We could also consider more outside forces that might act on the star to make the trajectory more accurate. We were asked to explain the difference between the net force and the rate of change of momentum. Based on Newton's second law, the net force is equal to the rate of change of momentum, and this is true for both the parallel and perpendicular components. The rate of change of momentum is basically how momentum changes over time, and net force is equal to all of the forces acting on the object. If a different black hole was placed in the same location of the black hole whose masses we found, and the motion of the observed star remained unaltered, and the gravitational forces remained the same, then we would not be able to calculate a different mass for this new black hole. This is because the mass was calculated based on the force of the change in momentum of the star. So, if the momentum of the star remains unchanged and there are no new forces acting on the star, the calculations will be the same and the mass of this new black hole will equal the mass of the original black hole. In conclusion, we can state that Newton's second law and the momentum principle are very useful when predicting the motion of an object. Also, based on this lab, we determined that we can calculate masses of unknown objects based on other objects' motions. Have a great day.